Hey everyone, my name is Miss Hu and I am a physics teacher. Now in this video, we're going to be learning how a force is induced on a current carrying conductor in a magnetic field. Now, just to let you know, the reason I'm using a Jamboard here is because I'm more of a Jamboard slash whiteboard slash blackboard slash chalkboard kind of teacher compared to being a PowerPoint kind of teacher. And the reason is because I usually like to scribble as I'm teaching, and I believe that as you observe what I'm writing and scribbling, it actually helps you build your logical thought processes so that you never need to memorize concepts again. Once you understand how the flow goes, it is easier for you to recall what you've learned. So in this video, the lesson objectives are: we will be learning how a catapult field is formed, how a force is induced on a current carrying conductor in a magnetic field, how to use Fleming's left-hand rule, as well as the factors which affect the induced force. So let's go into how a catapult field is formed. First things first, we need to understand the magnetic fields that exist. So let's take a look at some permanent magnets. So in this diagram on the left over here, you can see that we have two representations of magnets here. So imagine you have two permanent magnets placed at a distance from each other, and we have the opposite poles facing one another. So on the left we have the North Pole, and on the right side we have the South Pole. Now, as you already know, the permanent magnetic fields that exist here would of course all be parallel straight lines. So now, it's not easy for me to draw straight lines with my tablet, so just use your imagination here. Imagine that they're all straight, okay? So we've got permanent magnetic fields, parallel lines over here. Now, of course, we have the curved lines at the top here. Imagine, of course, that they look better, but you get the idea, right? So we have the magnetic fields that exist between the permanent magnets that look something like this. Now, you have already learned as well that any wire or conductor that carries current also generates magnetic fields around the wire. So the circles here, they represent the cross section of a wire that's carrying current in this case. So imagine if, let's say, this was the wire with current flowing through it, and the circles here represent a cross section. That means if you're looking at the wire from this point of view, you see the circle, right? That circles, the circle represented here, the circles over here represents the cross section of those wires. So these are two different wires. Now, I've got two circles set up here because you have to recall that the symbols used to represent the current direction are like this. So if you have a cross, so this cross, let me draw a better looking cross. Okay. So if you have a cross, the symbol here, the cross here represents current flowing in to the paper. That means if you're looking at it from this way, the current is flowing in or away from you. So into the screen in this case. If the current was flowing outwards, that means towards you, the symbol is like this. So this is flowing out of the screen. So sometimes when you're doing your exams, it would be into the paper, out of the paper, because if you're looking at your exam paper, so current flowing into the paper, yeah, that will be a cross. Flowing out of the paper, that will be the dot. Okay. So we know that any conductor that has current will generate magnetic fields around them. And because the wire is circular in shape, the magnetic fields formed will also be circular in shape. So I'm just going to use the circle function because you don't want to see me draw circles with my tablet, because you really can see that, yeah, drawing straight lines is already a challenge. Let me make this transparent. Hold on. Okay. So I'm going to just put this, I'm going to put this as a different color so that you can visualize the difference here between the wire and the actual magnetic fields. So we've got circles here. Let me put this a different color compared to the soft magnet. Yeah. And I'm just going to make multiple circles here. Making this slightly larger. Now, the further away the magnetic fields are from the wire, the weaker the magnetic fields would be. So the spacing between the circles are not exactly equal. The further away they get from the wire, the further apart they are, because the magnetic fields decrease in strength. Okay? Now, to determine the direction of the magnetic fields, if you recall, you use the right-hand grip rule to determine the direction. So in this case, because current is flowing into the paper, you'll find that the magnetic fields are going in a clockwise direction. So I'm just going to draw some arrows here to indicate the clockwise direction, like so. Now, if current was flowing out of the paper, let me just do this again. Over here, we will also have circular fields, but obviously the magnetic fields will be going in the opposite direction. So I'm just going to draw more fields here so that you can visualize. This is what the magnetic fields should look like. You get the spacing a little bit more correct looking. Okay, there we go. And this time, because current is flowing out of the paper, so towards you, you'll find that the magnetic fields are going in an anti-clockwise direction. So just to indicate the directions, I am going to draw the fields with the arrows as such. So what this slide is showing us is to remind us that yes, there are magnetic fields that exist between the permanent magnets as well as around a current carrying conductor. Now imagine that we take one of these conductors and we place it inside the field between the permanent magnets. So we've got this wire here. Let's have the current flowing inwards for this one. Okay. So if we recall the magnetic fields that exist here, first of all, we have the magnetic fields between the permanent magnets. I'm just going to sketch the basic magnetic fields first, which are the straight line magnetic fields between the north and south permanent magnets, and the magnetic fields that exist around the current carrying conductor, which are circular. And if we recall, in this case, they're going clockwise. So this is just a sketch here. It's not a proper drawing because this is merely a guideline for us to be able to predict what's going to happen next. Now, you must remember that magnetic field lines, in this case, are magnetic forces. And the magnetic forces can never, ever intersect like this. What's going to happen is that they're going to interact. So imagine if you have the forces interacting each other, if they're in the same direction, they're going to combine into the same direction, or if they're going to clash, they're going to cancel each other out. So remember that force fields do not intersect, they will interact, either to attract each other or they're going to repel away from each other. So let's take a look at what's happening here. So you have on the top, you find that, hey, the field lines happen to be going in the same direction. Whereas below the wire, you have fields that are clashing against each other. They're going in the opposite direction. So what's going to happen here is that you will find that the magnetic fields are going to, let's take another color. Let's take black now. So let's imagine it this way. The fields from the North Pole are going to try to go to the South Pole. So the fields here, you find, hey, we're all going the same direction. So they're kind of like, going together in the same flow. But underneath, it's fighting. The magnetic fields from the wire are going the opposite direction. They're going to fight. So like, you're blocking my way. So what's going to happen is that they're going to try to avoid that and take the easier route, which is going above the wire because the field lines are going in the same direction. So as a result, you'll find that there are more fields going above the wire than below. And this causes an unbalanced force above and below the wire. So taking a look at the black color lines, you'll find that the field lines above the wire are far stronger compared to the field lines below that wire. So I know this is pretty messy, so let's just clear this a little bit. So I'm just going to erase all these lines. And I want us to visualize one more time what's going to happen. So we have, again, this is current flowing in. We know the field lines are going in a clockwise direction. So the resulting field that we will see here is the fields from the North Pole are trying to go to the South Pole. They're going to go above the wire before it reaches the South Pole. And this is what will happen for many of the magnetic field lines. So underneath, of course, it may try, but because of the clash, it's going to try to avoid as much as possible. So there'll be a lot less lines below this wire compared to above. The unbalanced field lines here will end up creating a force, because you have to imagine it this way. Now the forces are not balanced. Remember that the greater force will always push towards the weaker force. Or another way to think of it is, now they're not balanced, they're going to try to become balanced again. So I want you to imagine it this way. So all these lines are straight at the moment, and because we have caused an unbalance, it will try to push away that thing that's creating the unbalance to become balanced again. So this creates a force that will push the wire out of the way. This is the force that has been induced because of the interaction between the magnetic fields of the permanent magnets and the magnetic fields around the current carrying conductor. This resulting field creates a catapult effect, and that's why this is known as a catapult field. It behaves like a catapult. So you know what a catapult is, right? It's like when you get this rubber band and then you put an object in between, and then when you pull and you release, the object flies. So this creates an effect just like this magnetic force. So that's why this is known as a catapult field, because it creates a force just like a catapult. So of course, for physicists, we would like to be able to predict this direction of force more easily all the time. We don't want to keep drawing magnetic fields and try to figure out the catapult field and all that direction. So this is where John Ambrose Fleming came up with Fleming's left-hand rule. How to use Fleming's left-hand rule? So you gotta, of course, use your left hand, and what you do is you have your gun, your thumb and your index finger here, and then think of it as you need a trigger finger. So the angles between each of your fingers and the thumb must be 90 degrees. It must be 90 degrees this way, must be 90 degrees this way, as well as this way. So you kind of form the edge of a cube. So why he came up with this rule is so that it's easier for us to predict the direction of the induced force all the time. How to use this? Your thumb will represent the direction of the force that's been induced. Your index finger represents the direction of the magnetic field from north to south, and your middle finger will represent the direction of the current. So here, this is a diagram. Thank you to Electrical For You for this diagram. So here is how you use Fleming's left-hand rule. You won't be given the direction of the force normally. However, you will be able to see the magnetic field, and you should know the direction of the current. So what you do is you line up your index finger with the magnetic field pointing from north to south, and you line up your middle finger in line with the direction of the current flowing in the wire. Where your thumb points to, that's the direction of the induced force. So you can see over here, what you do is this. Okay, so north to south, so point your index finger pointing north to south. Follow the current direction, you'll find, hey, your thumb is pointing upwards. That's the direction of the induced force. So how you remember it is this way. Thank you to phy.hk for this amazing diagram. So your thumb represents the magnetic force, index finger represents the magnetic field, and the middle finger represents current. Here's my way of remembering what each thumb and finger represents. So because this is force, so this will be F, this will be M, magnetic field, and this will be current. So I always tell my students, feed my cat, right? Because F from feed will be, of course, force, M, my, would be magnetic, and C, cat, represents current. Now, of course, you don't have to use my mnemonic here. You can always come up with your own. It doesn't matter as long as you remember what the thumb and fingers represent correctly. Here's another way. If you don't want to feed my cat, you can also use FBI. How it works is similar. So F in this case represents, of course, force. B would be representing bar, which is the magnetic bars. And I is the symbol for currents. If you recall what you've learned in electricity, like V equals IR, for example, V is potential difference, R is resistance, and I is current. So some students like to use this as well because it sounds so cool. Hey, FBI. Whichever mnemonic you use, it doesn't matter as long as you have remembered what the thumb and fingers represent correctly. To use this Fleming's left-hand rule, remember to line up your magnetic field with your index finger and the current with your middle finger to check where the force will be acting. You can also use this to check, hey, is my catapult field correct? So what you do is, okay, get your index finger to point from north to south. Your middle finger represents the current. So in this case, current is flowing into the screen, so get to point into the screen. You'll find that your thumb is pointing downwards, which is where the force will be acting. Correct, right? So once we've understood this, we also just need to run through quickly what are the factors which affect the induced force. Let's start with considering the factors which affect the magnitude of the induced force first. If you don't know how to determine what the factors are, here's a very simple way. We already know that the reason why the force is induced is due to, number one, the magnetic fields between the permanent magnets, and number two, the magnetic fields that exist around the current. Now think about it logically. If the magnetic fields have been changed, that's also going to change the force. And likewise, if you change the current, that results in a change of the magnetic fields around the wire, which also results in changing the force. So where am I going with this? So instead of memorizing factors, just need to take a look at Fleming's left-hand rule and think of it this way. If the force is the resulting action, that means this is your responding variable. If this is your responding variable, we know that these two will affect this. That means these two will be your manipulated variable or your factors. So if we are looking for the factors which affect the magnitude of the induced force, then the factors for sure will be the magnitude of current as well as the strength of the magnetic fields of the, I fail in my spelling, strength of the permanent magnets. Let me adjust this so that this looks better. There we go. Now, you also need to be aware of how the direction of the induced force can change. Same thing. You know that this direction changes with the direction of the manipulated variables. So which means that if we are considering the direction, the direction of the induced force will depend on the direction of current as well as the direction of the permanent magnetic fields, which means where the north and south are. So here's a recommended video which I encourage you to watch to gain further understanding about how the force is induced. It's by physics.org, and in this video they give a detailed explanation as to how the force is induced, complete with a video that they've taken in the lab to show you in a practical sense how the force is actually induced. So it's really exciting. For my video explanation, I'm just going to play a few seconds snippet. But please, I encourage you to watch this video. The link is provided right on top over here as well as in the description. So let's take a look at this video. I'm just going to move my face out of the way. And I want you to observe. So over here, they have the copper wires. So the wires are there because we need to have a connection between these wires, which are connected to a direct current circuit, as well as this free moving piece of copper wire. Because this wire is going to move, we need to have direct connection between this wire as well as these connecting wires which are to the circuit, because we need to have current flowing through this free moving piece of wire. This free moving piece of copper wire is placed between two permanent magnets, so one is north, one is south. It doesn't matter which, as long as they're opposite poles, in order to create a magnetic field that will induce the force. So let's play this video on the section and let's see what happens. So you can see that the force has caused the wire to move. Let's watch that again. And there you go. So if the current is less, of course the force is less. That's why the distance traveled is less. If the current is more, the force induced is also more, so the distance will be greater. And in this situation, the magnets have been reversed. Let's watch that again. So you can see that because the magnets have been reversed, the force is also in the opposite direction. So if you want to watch this video in full, do check out the link that I have shared in the description below. So I hope you have found this video educational and helpful in understanding how a force is induced in a current-carrying conductor in a magnetic field. Thanks for watching. Don't forget to click like and subscribe to my YouTube channel, Physics Rocks. Happy studying!